Okay. Hello, everyone, and welcome to iWebScience webinar on weather files and building performance simulation. To introduce myself, I'm Ranjit Jebalandaya. I wear a number of hats for iWebScience. I'm one of the board members and also editor of our newsletter. And as for my profession, I work as a consultant engineer at Design Builder. Before I move on to introduce our speakers, allow me to mention that if you are not a member of iPepsa England, you can become one for free, and we will keep you updated on the latest news, events, job opportunities, etc. And shortly, I will post a link on the chat box, which you can click on, go there, and become a member for free. Also, during the webinar, if you have any questions, please post them in the Q&A box and not the chat box. I repeat, please post any questions you may have on the Q&A box and not on the chat box. And we will try to answer as many as we can at the end. Okay, now to introduce our first speaker. So we have Nishesh. Nishesh is a research fellow at the Institute of Environment Design and Engineering at UCL. He researches in the field of energy modeling and operational performance of buildings, and currently in collaboration with Design Builder is developing new tools for operational performance assessments. He's a qualified architect, and for many years, he has been involved in performance simulation related consultancy and research. With that, on to you, Nishesh.
Thank you, Ranjit, and welcome everyone. It's in today's presentation, I'll be talking about weather files and their use in simulations, how to use different types of weather files correctly, where to get those for your projects, and also I'll be introducing a new weather tool from Design Builder called Climate Analytics. I'm Nishesh Jain, and I'm a researcher with University College London and Design Builder software. So at the end of this presentation, you should have a better understanding of different types of weather files used in energy modeling. And also you will have a clear understanding of what weather data to use in different energy models for different applications. I'll be covering different types of weather files, how they are used in typical simulation applications, and most importantly, where you can get reliable weather data for your models. So where does the data come from? And how are these files created? Until recently, most weather files used in building simulations were clearly created based on historic readings, and they're coming from weather station measurements for scattered locations. But as greater emphasis is placed on design for optimal performance using realistic weather specific to the project and for specific purpose, the integration of weather data into simulation process is integral. For example, in the current context of climate change, only using a typical year weather data for designing tomorrow's building may not be ideal, as the building needs to perform well in future climatic conditions as well. So the current best practice modeling requires use of accurately measured weather data with options to support all different types of building performance simulations, typical analysis, extreme events, and future scenarios as well. The reasons to use weather data in simulation covers a wide range of applications such as design stage, energy and environmental performance projections, or heating and cooling sizing calculations, testing resilience against future climate, developing calibrated models, and even doing climate-based daylight analysis. The most used weather files are for typical analysis using typical years such as TMY and TRY files. These files are purely based on historic readings and has been used and is used historically recorded places and locations. The other weather files that are being used are design years and actual years, and therefore, for example, for extreme scenario modeling, you would be using design years, These may be for post-processed data with extreme weather projections, or even an actual year where extreme weather data has occurred. In post-occupancy measurement and verification studies and calibration applications, the actual weather files are used and are often for that specific location. So where you can find these data, you can get the data from typical files from typical weather stations as standard, such as from the Energy Plus weather data available. However, there are now these global weather data sets provided by organizations such as NOAA and NREL, and even satellite measurements. The images here are from the NOAA Integrated Surface Database with its locations. However, these are general purpose weather files and not configured to the specific locations used in typical simulations that we do. The data is stored in different formats, and there is no quality checking as such for suitability or correctness. To bring this type of data for building performance simulation purposes, Design Builder has therefore developed a comprehensive weather data tool called Climate Analytics. Pulling in data from various databases, while NOAA and NREL and satellite measurements provide the baseline data, Climate Analytics brings it together for you to download in EPW format for use in energy models. As mentioned earlier, most data sets are not perfect and require sanity checking. Climate Analytics has internal checks to ensure that the weather data is checked, cleaned, and then made available for use. And while you have access to tens of thousands of locations, you can also generate hourly weather data for a location that does not have a station listed on the map. Interpolation between the nearby stations based on distance can get you hourly weather files for almost any virtual location. With access to reliable and comprehensive databases, you can generate all various types of weather files that you may need, starting from typical years, TMY and TRY files. These typical years are representative of long-term weather compiled from 20 to 30 years of data, and they match long-term data trends from that particular location. Typical weather files usually use real data, but may be not from a contiguous year. TMY files contain data comprising from multiple years, such as for this Chicago TMY file, we have some months from 1980s and some as recent as 2010. Design years usually contain a specific year of weather data that has some extreme characteristic associated with it. These design years are used for cooling sizing. Might be years where there has a strong heat wave with a warmest run of 4 days, or it's an overall warmest year. One of the applications of design year data is for overheating analysis for naturally ventilated buildings. Overheating assessment is complex, and weather files being used may change depending on the overheating calculation methodology. For example, overheating calculation required by SIPC have a specific design summary or file, DSY file for future. These are specifically created for overheating studies and have long hot summers to account for what might happen in future, but the winter weather data in those files is not projected for the future. Therefore, those files should not be used for annual simulations for future climate. Analyzing data trends can help you also select the year that you may want. Looking at design year files, you may want to use in your performance analysis for extreme events. Then, for example, this min-max average graph for temperatures shows that the coldest and warmest temperatures recorded for this location were in 1980s and early 2000s. However, the overall coldest and warmest years were more recent in 2014 and 2012. So you can choose accordingly or analyze some other longitudinal data trend. I'll cover use of some similar graphic longitudinal data analysis in slightly more detail towards the end of this presentation. For this case, the coldest year 2014 had a cold winter but also cooler summers, whereas the warmest year 2012 had hot summers coupled with warm winters. Comparing that to a TMY file, typical year is somewhere in between. Therefore, typical years can give the best average trends but should not be used for system sizing, for example. Data from typical design files can further be post-processed by adding future climate projections using projection models from for various future emission and probability scenarios. These projection models are typically based on IPCC scenarios provided by organizations such as CISRO, Hadley Center, etc., and are used to modify weather files accordingly. Another post-processing you can do is for urban heat islands. For your weather files, you can add a day or night time offset for dense urban areas and maybe subtract these offsets if your location is rural and the station is in an urban setting. These day and night time offsets are from NASA database for that specific heat island area. Actual years contain specific year weather data. The most common use is post-occupancy measurement and verification studies and developing calibrated models where simulation results are compared to actual utility bills or other measured data. Actual years can also be used as a part of more thorough approach to design or energy analysis. While the climate analytics database covers over 43,000 stations, there's always an interpolation option that allows you to generate actual weather for a precise location as well. However, there is more to climate analysis than just the weather files itself. With so many options, you can and should ensure that you are using the appropriate data. Typical and actual years are straightforward, but for design year selection, it's a key step in your weather file. And that depends on the application. As mentioned earlier, an important application for design weather is overheating assessments and HVAC system sizing simulations. However, there are various ways to define what a cold or a warm year is. So it's important to clearly understand what design weather data is required for your simulations. For example, should you use a year with highest dry bulb temperature average or year with highest instantaneous temperature or with one which has the most extreme heat wave? In that case, how would you define what the heat wave is? Will you use the maximum temperature or the daily average temperature? How many days would you consider as a heat wave? 4 days, 10 days, 20 days? Does it account for humidity? So assessing the longitudinal climate can help you select a design year for all of these cases. These are the graphs from climate analytics for a Nottingham location. It illustrates the three methods that can be used to define warmest year based on dry bulb temperatures. The left-hand graph we already looked at. It shows the maximum, minimum, and average hourly temperatures for the year. So in the orange, blue, and the green lines respectively. The graph on the right shows the 1 to 4 day heat wave periods. The top set of 4 lines show the maximum daily temperature averaged over warmest sequence of 1, 2, 3, and 4 days. This data can be used to quickly identify the years with most extreme heat waves based on maximum daily temperature. Now, this may be ideal design data to use for commercial building applications, which are generally occupied during daytime when the temperature peaks occur. But for residential buildings, I would ideally generate graphs with heat waves based on average daily temperatures so that the nighttime periods are also included in the heat waves. So this is a summary of various ways to identify warmest years. The top 3 ones, as I mentioned earlier, the year with high all-time temperature, the average high, and the 4-day heat wave. Then the table also shows years that could have been selected for 3 other ways that hottest year for this location can be selected, including the average maximum or the extended heat wave. As you can see, each method indicates a different year. So the takeaway point is that you should consider what is likely to be the worst case weather scenario for your project and choose your design years accordingly. However, it won't always be clear which selection method to use. In that case, you can explore a range of worst case years to see how the building performs using parametric analysis. With the available data, historic weather data can also be reviewed for climate trends at a more granular level, and also looking forward in time for future climate change models and for comparing the offsets for each of these. Climate analysis is not just limited to temperature, but can also include solar intensity, humidity, wind speed, or precipitation data for other applications on annual, monthly, or daily basis for further downstream analysis. The final aspect, whether to assess whichever weather data you are working with, is to check the quality of the base data and the design and the actual design data being generated. You need to look for missing information, outliers, etc., and then see how they are handled with the final weather file. So this covers some of the key analysis that you can do as a part of the rigorous data selection process. So climate analytics is now available. If you wish to explore some of these, then a lot of these weather files and analysis tools are available there. Try it out by going to the hyperlink on the screen, analysis.designbuilder.co.uk. Thank you.
Thank you, Nishesh. I can see a couple of questions on the Q&A box. We'll answer them at the end. If anyone have any questions, please do post them on the Q&A box, and we will try to answer as many we can at the end. With that, we move on to our next speaker. So our next speaker is Sukumar Natarajan. Sukumar is a professor of environmental design at the University of Bath and director of the Center for Regenerative Design and Engineering for a Net Positive World. He was elected fellow of IPIPSA in 2022 for services to the community. He has been undertaking research on weather files for building simulation for over 2 decades, in addition to work on related areas such as energy efficiency, carbon, indoor health, and thermal comfort. So with that, I'll hand over to you, Sukumar.
Thank you. I trust everybody can see the thing. It looks okay. Excellent. Okay, so hello everybody. As Ranjit just said, I'm Sukumar Natarajan. I'm based at the University of Bath. And I want to thank IBIPSA England for inviting me to speak today about our work. And it's really nice to be amongst friends. Nishesh and I have known each other for more than a decade, I just worked out. So it's a wonderful honor and privilege to speak alongside of him, and also to briefly thank our many funders, primarily EPSRC here in the UK, but also the Department of Science and Technology in India, and then the Coalition for Disaster Resilient Infrastructure, as also our research partner in India, which is IIT Roorkee. Okay, so with that out of the way, I don't think I'm sort of necessarily recapping in any serious way what Nishesh said. I'm sure many of you are aware, so we need weather files in simulators such as Energy Plus. Pretty much any building simulator, you require the starting point is what weather you put into it. And I've said here building energy consumption, but it goes through for all the different types of analyses that Nishesh has alluded to. And exactly as Nishesh pointed out, that climate and weather, it can be very variable across a landscape. So what you've got to work out is how far away the nearest weather file is. And historically, we've not had a good sort of localization of weather files. And that has been shown, it doesn't always produce a 2x error in estimating annual energy use, but it can absolutely happen. And it can happen at relatively short distances. You think, the weather file is, 50 kilometers away, should be fine. But if it's near a particular geographical feature, such as a hill or a lake or whatever, you could be quite badly off. And the problem with using observed weather data, which has been the sort of historic basis on which we've done these things, is that the spatial resolution is, very much dependent on where somebody has found a pot of money to put up a weather station. So you might get a lot in a particular area, and then you might not get any. So you might, if your building is not near one of these sites, it can be a bit of an issue. Even when you do get data, it's not always in the way that you want it. There might be gaps. The recording period might be, say, daily, for example. So you get a daily max and a daily min, and you don't get the intervening hours. So as you might be aware, in Energy Plus, you need hourly weather data. So there are problems on the time domain as well. And sometimes there are problems in terms of completeness. So the cheapest way of measuring some aspect of the weather is to measure temperature and humidity. But the moment you add things like solar or wind, it gets a bit more expensive. So there are, as you try and expand the range of variables of interest, which we need all of them, as Nishesh pointed out, for solar analysis, daylight, and all the rest of it, natural ventilation. As you expand the envelope of variables, you find that actually there are fewer and fewer stations hosting those variables. So we've got a problem of access. And if I just show you what the historic state of the art has been and almost continues to be, in a sense, in the UK, that is 14 locations. There have been updates, so this is not a static picture. I think the historic norm was just 14 locations with observed weather, but I believe now with morphing, you can get future weather for these 14 sites. If you average out what 14 is over the land surface area of the UK, that's about one weather file on average per 132 kilometer square boxes. Okay, so your nearest weather file could be rather far away compared to where you are. In fact, if you notice, there is no weather file for Bath. I have to use one for Swindon, probably, or choose one on the coast in Cardiff. So it's not ideal. And this exactly the same problem in India, a much larger country. So you can see there are 59 locations. But that actually works out to 236 by 236. If you evenly spaced out everything, that's the sort of thing. So the picture on the right is a much bigger landmass than the picture on the left. It's the first message. So once again, so there are 59 locations. This is the official data set sitting with ISHRE in India. And the basis years are often, maybe 12, 15 years, whereas really you want 30 years worth of data to produce a proper weather file. So, and once again, a lot of the data on the solar front are imputed rather than observed, simply because these data don't exist. So, and just to zoom in there on the right-hand side, this particular part of India, just to illustrate the problem that can occur. So this is the eastern state of Odisha, and that's a topographical map there on the left. And the only weather file for this is a coastal weather file for the city of Bhubaneswar, which is one of the red dots there. And if you're putting a building up in a city in the same state, you might be on the other side of a mountain, quite far away from the coast. You might be near other features. and you don't have much recourse. I've purposely chosen a slightly more extreme example, but there are maybe another weather file near Rourkela, but it's still triple digits, 200 kilometers ish. So it's very difficult to work out which one you could use, but you'd be almost certain that whichever one you chose is unlikely to be of very good value to predict, reliably understand the performance of your building on that site. Okay, so and the problem being that you need something like 30 years worth of hourly data, which doesn't exist in most locations in the world, really. I know there's more and more data coming along, but even then, once you really zoom in to a piece of land, you find that there's lots of gaps. So when we began work in this area, we thought that one way to solve it would be to produce synthetic computer-generated weather files. And we began this program of work about a decade ago. So around the time that I met Nishesh was when we were beginning to work on this. And that particular project was called Colby, which stands for the Creation of Localized Current and Future Weather Files for the Built Environment. So this was funded by EPSRC in the UK. And the India work, which started in 2017, was funded under a project called Zero Peak Energy Building Design for India, which is 50% UK funding and 50% Indian funding. The weather files part of the work is only one component of that India project for those who are interested. So what did we do with the UK project, which is the older project in this list? We use something called the Spatial Urban Weather Generator, which is the updated version of the UK Climate Impact Programme weather generator. Essentially, it's a stochastic tool that generates a precipitation sequence for a given small patch of land, in this case, 5 kilometers by 5 kilometers. And from this precipitation, it then works out the other variables based on known intervariable relationships from the baseline climatic data over the so-called control period of 1961 to 1990. And then the probabilistic climate change projections are formed. So essentially, it's a continuous thing. So you can take it to produce different slices of weather for past, near future, middle future, and future, distant future. And this is using a set of climate models, regional and global. The beauty of the Spatial Urban Weather Generator, the SUWG, is that it also takes into account impacts of land use. So elements of the UHI are implicit within the data that the weather generator produces. One of the limitations of that weather generator at the time that we used it is that it was only producing the medium emission scenario, which is the SRES A1B. In modern parlance, it's somewhere between the RCP 4.5 and 6, RCP standing for Representative Concentration Pathways, essentially tells you how warm the world is going to get in the future. The larger the number, the more warming you're expecting. These are global warming potential watts per square meter, I think the 4.5 and the 6. Okay, so this is not the hottest vision of the world, but a sort of medium hot vision of the world. So it's not like we're trying to scare people. And it's sort of, I think even if it were available, we would have, if other options were available, we would have probably chosen this particular type of scenario anyway, because otherwise, people get rather frightened when they see crazy weather. Although we're getting less and less frightened as time goes by, which is interesting. On the India front, we went to the UK Met Office, which plays a role in the UK CP, the weather generator work that I showed earlier. And here we chose to directly use outputs from one of their regional models. So they have a global scale model, which is called HAD-CM3, and then that is then downscaled to 25 kilometers using a regional climate model. And the data are called PRECIS, PRECIS, and it's providing regional climates for impact studies. And the reason we did this is because we couldn't find a reliable weather generator for all of India. So one of the key goals for all of this work is to try and be consistent. So we can't use different weather generators for different parts of the country. But eventually we realized there was actually enough data within this data set for us to produce our work. Because what you get are 17 equiprobable members, which simply means there are 17 versions of reality, and it starts from 1st of January 1970 and ends at 31st December 2099. And you get it for all land parcels over the country. And like the UK work, this is once again the A1B, the medium-high emissions scenario. It's taken us a long time to get this right, we hope, because we had to spend a lot of time doing quality testing, calibration, and so on. I'm just going to highlight some of the things we had to do. In Prezi, we get 3-hourly solar data, but we need hourly. So there was a whole bunch of work we had to do to get that right, and then calibrate it correctly. And then the non-solar data was calibrated using observed weather data from 400 stations in India. And that covers temperature, humidity, and wind speed. That was not a trivial exercise. It took a long time of careful study and a lot of analysis to do it. Because when you're dealing with large quantities of data, many of the time it just looks just fine, and then suddenly you find an error and then realize actually the stuff that looked fine wasn't that fine to start with. And because we wanted to make sure that everything was well behaved, consistent, we then used the data, this calibration data from 400 stations, and using a technique called multivariate kriging, which is a weighted interpolation technique, a bit like what Nishesh was just referring to earlier, in their service. It's a similar sort of thing. It's a weighted interpolation technique. And we ended up with data on 4,790 sites. Okay. But anything over 1,000 meters, we weren't confident with the data. So we have the data, didn't always look good. So we kind of put an arbitrary threshold of 1 kilometer above mean sea level. So everything below that, we can supply you with the data. Anything above that, we can't. Okay, so what did we get for Colby, the UK? We get 5 kilometer grid resolution, current and future weather files. That's 11,326 locations. Just throw your mind back to what is the current state of the art from 14 to maybe 35 to 11,326. So we think it's a dramatic improvement. And what do you get for each of these locations? You get a test reference year, which, as Nishesh showed, is a composite year. So a January from one year, a February from another year, a March from another year, or whatever. You get 12 months that are stitched together to form these typical years. And these are probabilistic, so you can select them based on the median, the 10th percentile, or the 90th percentile. So here's a picture of what that looks like for the UK. So this is a map for the 2080s for all of the UK. On the left-hand side is Tmax in that year. And on the right-hand side is Tmin in that year. When these data first came out and we shared it with colleagues in industry, they just said, well, come on, this is ridiculous. We're not going to get 40 Celsius plus in London. But as if any of you are sitting here in Britain, you recall, I think London hit 40 Celsius 2 years ago. So in some ways, you could argue that these data are already quite conservative. But that's kind of how our knowledge of climate change is changing and how the weather is changing. I was about to say under our feet, but actually over our heads. The weather is changing and the climate is changing all the time. In addition to these 3 weather files using standardized methodology, test reference year, you also get some descriptions of extremes. You get design summer years, which are sort of 3rd warmest year in a period. So it's the median of the upper quartile. So I think Nishesh alluded to these in his presentation. You get something called the supersynthetic heat wave, And this was a sort of reverse engineered process where we actually don't start with external conditions. We start with bad internal conditions and work out what weather would have caused those bad internal conditions. So essentially, we have a thermal model of a building, and then that is then put through a stressing procedure, and we kind of work out what the heat wave would look like. So it's a sort of puts the focus on indoor conditions rather than outdoor conditions, which is kind of what most of us care about. I put the PTRY max and PTRY min within little tildes to just remind myself and you guys that they are not really pictures of extremes as such. They're just typical hot and typical cold periods in these weather files. And of course, you can use all kinds of you can do all kinds of cool stuff with these data. This is analysis of gas use for space heating across the UK. On the left-hand side is the 1970s, in the middle is the 2080s, and in the right-hand side is the difference map between these two. Moving to India, once again, you get the same test reference years, but now at 25-kilometer grid resolution. And the 50th percentile map now looks like this. The black dots, just to remind you, are where that's the current state of the art. And everything else is the new stuff. We also came up with these Indian peak years. There's no reason to call them Indian peak years. We thought it was fun to call them Indian peak years. They're essentially 7-day extreme events. So they're a continuous year. So they're not artificial years. They're an actual continuous year of data with no breaks or anything, but that contain one extremely hot or extremely cold 7-day period. And it's not just dry heat. You essentially also select on wet bulb temperature extremes, which is also very interesting. Once again, to show you what Odisha looks like, the state on the eastern coast that I showed you, you can see here on the left, that's the sort of current, in quotes, weather, and then on the right-hand side, the future weather. The main takeaway from this is that the 25 kilometers is meaningful. The spatial resolution is meaningful, and you can see between adjacent grid cells, you don't get the same outcomes, although in some places are more similar than others. How are we doing for time, Ranjit?
Can take 5 more minutes.
5 more minutes. Awesome. I'll try not to rush too much, but I don't think there's a ton to say. Here's another couple of examples. These are 3 cities separated by 50 kilometers each. They're actually sitting on the plains where you're not expecting massive variation, and yet you can see some of these cities are closer to water bodies, others closer to hills. So on the left-hand side is a flood plot. Top row is the present period, bottom row is the future, and you can see there's a difference between these two. I just want to point out that the scales are different. So just to say, bottom left graph tops out at 48.2, bottom right graph tops out at 46.3. So there's a 2 degrees Celsius difference in the range. And here's the third city. So, if you were using the same weather file whilst you were putting buildings up in these different cities, you could be doing, you could be getting the wrong estimate. And we're very careful in case of the 7-day extremes that I just described to tell you about the quality of the data you're getting. So there are comment files in the EPWs that we use to tell you that how extreme the 7-day period is compared to the worst period, the comparable worst period in the typical weather file. Okay. And once again, those are just pictures of the dry hot and dry cold series for current and future for the same 3 cities I showed earlier. And you can see these are not the same, and assuming they would be the same could be, in some cases, not terribly catastrophic, but in other places more catastrophic. And certainly the warming trend at nighttime is very, very stark. Nights are maybe 5-6 degrees warmer than they have been in the past. And I think this is the last but one slide. So this is the same analysis now going back to Odisha, which is on the eastern seaboard. This is degree hours of cooling degree hours using either dry on the left or wet bulb temperature on the right. And you can see there's quite dramatic changes. Top row is the past, bottom row is the future. And you can see there's quite a lot of change on the wet bulb front for this particular part of India in the future. So that brings me to the end, and I just want to take the last 30 seconds to thank all the many, many colleagues over many years, more than a decade worth of collaborations. David Coley, who started out the Colby project, and I worked with him on it. Oliver Hatfield, he was a postdoc on our India project. Sanoba, another postdoc, now a senior lecturer at De Montfort. Hangyol Park, who's was a visiting researcher from Korea, came for 3 months, didn't realize she was going to be working on this. And then all our colleagues from Roorkee, especially Rajasekhar, who's the PI, and Shweta Lal there, she's the one who's made all the IPY files, those extreme 7-day weeks. And Nishesh and Andy from Design Builder, because they've been helping us very unselfishly, helping us to test the quality of our weather files, especially the India ones. Yeah, we really extend our heartfelt gratitude to all of these wonderful collaborators. Thank you.